Learning goal here, we want to recognize and use piecewise functions. And we're going to recognize them as a combination of multiple subfunctions with restricted domains. Right? Remember, domains, that's just input values. Okay, so the definition really of piecewise, or another word that describes piecewise, is a hybrid. And hybrid stands for many. Okay, similar to piecewise. Piecewise, many functions. Okay, and so this is how I read this example here. We've got this function, f of x is equal to 2x plus 4, so it's linear when x is less than or equal to negative 1. So if we can kind of just get a little visual here, if this was our graph, when x is negative 1 and less than that, okay, we've got a linear function. And then it's x cubed when x is greater than or equal to 1. So at this point here, 1, we've got x cubed. Okay, so we know x cubed something like that. Okay, so our cubic looking like this, and our linear function. Okay, we go. It's just something that looks like that. So here, evaluate f of 1. Okay, well, we have a look where for our function is it defined at 1, and when it's defined at 1, it's this guy here. So we substitute. So we substitute 1 cubed because it's x cubed at that domain specifically, which is 1. Alright, f of negative 2. Have a look specifically. Negative 2 is in the domain of this function right here, our linear function. So we'd say it's 2 of negative 2 plus 4, right, which is equal to a 0. Okay. Third one here, f of 0 equals, well, when on our function, this is our function, is 0 defined? It's not. Okay. So we'd say f equals 0 is undefined. There's no x values for x being 0. B, okay, we're going to state the domain and range of the entire function. Alright, so in order to do this one, I would need to just, I'm going to graph this. Okay, and so I know at the point of x being 1 right here, y is equal to x cubed, so that would be the point 1, 1. It goes up like that. Okay, that's y equals x cubed when x is greater than or equal to 1. At x equals negative 1, alright, we could determine that if we just did 2 of negative 1 plus 4, we'd get that's equal to 2. So at the point for y of 2, including that point, it's linear. And we know for every 2 we go down, we go 1 across. So it's got a linear function like that. We've got y equals 2x plus 4 when x is smaller than negative 1. Okay, so that's what our graph looks like. Once we've got that, we can sort of see our domain a little bit easier. Is there any input values that are restricted? Well, from negative infinity going all the way up from this way here for our x values, negative infinity is fine. We can put that in all the way through to 1, including it. Okay, and then we pick up negative 1, and then we pick up things again at 1 through to negative infinity. So that would be my domain. I can put in everything except the values between negative 1 and 1. Because these values here, these x values, there's nothing there. It's undefined between that point. And our range. Okay, well, our range is the list of I'll do range in a red, the list of output values. So we can get anything going below here for our output values, so we can go negative infinity, and then we have a look, is there any restrictions? So we can get all the way up to this point 1, we can get all these points in here for 2, from this lot in here, they're all output values, and then everything above that we can rely on this guy over here. So we've actually got no restrictions on the range. We can get any value out of the function, so negative infinity through positive infinity, that's fine. Okay, that's B there, stating our domain and range. Alright, then we want to state the interval for when f of x is not continuous. Okay, let's say f of x is not continuous along this interval here. Okay, so when x is between -1 and 1, okay,